Dear listeners, this is Aishwarya, Assistant Professor, Department of Chemistry, St.Josephs College of Arts and Science for Women, Husur. In this video, we are going to see about the F-block, F-block elements of lanthanides. So, lanthanides are four of block elements. The F-block inner transition elements containing partially filled 4F subshells are known as the lanthanides or lanthanodes because they have close similarity with the element of lanthanum atomic number 57. The 14 elements from the atomic number 58 to 71 is called as the lanthanides. So from lanthanum to lutetium. Positions of lanthanide in the periodic table. All the lanthanide have the atomic weight between barium and hafnium. Therefore, must be placed between these two elements told by Moseley. Barium has exactly same outer electronic configuration of calcium and strontium and resembles very closely. Similar way, hafnium is similar to zirconium. So, barium must be placed below strontium and hafnium below zirconium, thus leaving only one place between exactly below yttrium. Since all the lanthanides resemble one another in many respects, they must be placed in the same group. These elements also resemble yttrium because of the following additional similarities. The causes of lanthanide contraction. Electron in the f orbital repel one another so very weakly because of the lobes of the f orbitals are far apart from each other. The poor shielding effect of F electron. Shielding electron decreases in the order of s, p, d, f. Effective nuclear charge increases with increase in the atomic number of lanthanide. So the increase the inward pull the 4 electron of and result the reduction of the size of atom or ion. So this contraction is inward due to the higher nuclear charge and poor shielding effect of effector, the main cause of lanthanide contraction. So next, extraction of lanthanide from the monazite mineral. Monazite is the chief mineral from lanthanide are extracted. While extracting thorium from monazite, the lanthanide are obtained as the byproduct. So following operation are carried out in the extraction. The monazite stand is heat with sulfuric acid for several hours. Then we react with cold water to form the unreacted monazite, and it is the filtrate containing lanthanum thorium. It is neutralized and added the HF. Then it is the filtrate to form a lanthanide and phosphate ions. And in the lanthanide and phosphate ion treated with sodium hydroxide or oxalic acid to form the lanthanide hydroxide or oxalate. So general properties of lanthanides. They will shielded the 4f orbital. So there is no most appreciable change in the outermost arrangement of the electronic shell with increase in the atomic number. Oxidation state and oxidation potential. It is a insoluble compounds are given below, from which is noted the electronic configuration of lanthanide in the ground state. All the lanthanide forms the tri-positive lanthanide cation. The color and absorption spectra of lanthanum ions. The color and crystalline compounds of lanthanum ion persist in aqueous and non-aqueous solution remains unaffected by the change of anion present or by addition of colorless complexing agents. So the color of lanthanum ions is of the lanthanide ions colors. Then the consequences of lanthanide contractions. The first one, the steady decrease in the size of lanthanide ions. Second one is the slight increase in the electronegativity of the trivalent ions. The third one is the resemblance of second and third transition series. The radius of third series are about the same size of the second transition series. Its similarity of the atomic radius is due to the presence of a block near the beginning of period 6. Then the difficulty of the separations. So separation of elements is a very difficult task. Then the high density. The third transition series is a transition series is very high density, so it is responsible for the lanthanide contraction. The difference in basicity. The size of the lanthanide ion decreases regularly with the increase in the atomic number lanthanides. The bonding with the small cation and hydroxide becomes most covalent. The basic strength of the hydroxide decreases. This explains clearly that lanthanum hydroxide is strongest while ruthenium hydroxide is weakest base. The basic strength of oxides of lanthanides decreases with increase in atomic number. Magnetic properties of lanthanides. Most of the lanthanides are paramagnetic, presence of unpaired electron in their 4f subshells. Lanthanum, ruthenium, cerium, ytterbium are diamagnetic because they have no unpaired electrons. Thus, magnetic behavior in case of lanthanide arises due to the contribution of both spin magnetic moment as well as magnetic behavior. So, magnetic moment is equal to mu. The lanthanide, the spin contribution and orbital contribution coupled together give a mu quantum number. There are the two types of values. The unusual shape of the curve arises because when the F subshell is less than the half fill, the spin and orbital magnetic moment work in opposition, but when F shell is more half fill, they work together. The magnetic moment value of d block element is spin only, transition element is spin only value. Color of lanthanide ion depends upon the number of unpaired F electrons. Lanthanide ion containing NF electron often have a similar color to those with 4 and 14 minus NF electron. The color of the lanthanide ion due to the absorption of light from the visible region. These types of transition is called the FF transition. The FF absorption of lanthanide ions have low intensity because the transition are not allowed. The lanthanide due to the FD transition allowed very intense absorption bands. Example, cerium. The transition due to FD bands are broad contrast to narrow FF bands. The color of the lanthanide ions is due to the charge transfer. When the metal is high oxidation state, the ligand has the strong reducing properties. So the charge transfer usually produces the intense color. Strong yellow color of cerium solution arises due to the charge transfer. The color of lanthanide ions. The unique feature of spectra of tripositive lanthanide ions. Absorption bands are sharp-like bands in the UV visible region. The bands of lanthanide ions are very sharp, used for characterizing lanthanides. Transition elements DD transition gives the absorption bands whose position changes from ligand to ligand, and width of the peak is greatly broadened because of the vibration of the ligand. The lanthanide does not change with the different ligands. It shows the little depends of the nature of the ligands. The UV spectrum of the polonium ions.